on building geo-distributed applications with Redis conflict-free replicated databases. This is Cristina Cardoza, social media and editor of SC Times. Before we get started, I have a couple of quick housekeeping announcements. First of all, we will be conducting a live Q&A after today's presentation. If you have any questions at any time during the presentation, you can submit them through the control panel's question tab. Secondly, this webinar will be recorded and available on demand through the sctimes.com website in about 24 hours after the event. Today's presentation will look at how always-on AP-leaning deployment of Redis is possible with conflict-free replicated databases, as well as provide a demo on how to code an application with CRDBs for safe distributed failover across 2 data centers while avoiding any downtime. Here to discuss this further is Cihan Baykoglu. He is the Vice President of Product Management at Redis Labs. Cihan is a big data enthusiast who brings more than 20 years of experience to Redis Labs product teams. Prior to Redis Labs, Cihan was Director of Product Management at Couchbase and responsible for the Couchbase server product. He was also a part of the team in Redmond, Washington that launched Azure Public Cloud Platform at Microsoft, and he has delivered a number of versions of the SQL Server product suite. In addition, he holds a number of patents in the database field, and he has a Bachelor's of Science in Computer Engineering and a Master's of Science in Database Systems. Now to get things started, I'll turn it over to you, Cihan.
Thanks, Christina. Hi, everybody. I want to quickly go over the agenda of what we're going to talk about after that great intro. So we're going to take about 35 minutes or so to go over and introduce Redis and Redis Enterprise. Just in case you haven't heard of us, I want to introduce the product. I'm going to give you a quick overview of the core architecture and replication architecture, specifically in Redis Enterprise. Then we're quickly going to dive into CRDTs. If you haven't heard of this technique and technology, I'll give you a quick overview of what it provides and how our implementation enables a set of use cases that were harder to build in the past. We'll go under the hood on Redis CRDTs. I just want to show you how we have implemented the capability. I think it will answer a lot of the questions you might have as to how this capability works under Redis. We'll then look at how application developers would use Redis CRDTs to develop applications, and I just want to close off with a demo. We'll just walk through a couple of cases. We'll have a geo-distributed cluster. We'll simulate some failures, and I want to show you how the technology handles those failures. Finally, like Christina said, at the end, we're just going to do Q&A. I'm happy to take questions during the presentations too, but feel free to bring up any of the issues you see or any of the questions you have at the end, and we'll have plenty of time to go through them, hopefully at the end. All right, let's dive in. If you haven't heard of us, we're the company behind the Redis product. Redis is a leading in-memory open source database platform. It's used mainly for high performance operational analytical use cases around the world. It's in database years a fairly new engine, but it's taken over, and in terms of popularity, it's growing at an extremely fast clip. We're the home of Redis at Redis Labs. We provide the open source technology, but we also wrap this technology and enhance it for the enterprise mission critical applications. We call this platform Redis Enterprise. And as I talk through, I'm going to talk through what Redis and Redis Enterprise provides and how they actually work together. But the most important starting point is Redis and Redis Enterprise are 100% compatible. So applications that you develop on Redis open source can simply change their connection string and point at Redis Enterprise and continue to work, and the reverse is true as well. So let's get a quick overview of Redis and why Redis is so popular out there first. One of the most important reasons why Redis has become a de facto standard for a lot of people is its performance. It started as a database that is a caching tier in front of other databases that can't scale. So it's been that buffer. But over the last few years, we've seen Redis become a system of record database for many people as well because of its performance. It's known to consolidate the database and the caching tiers together, so nobody deploys a cache in front of Redis. And because of that ability, it simplifies development, and you don't have to deal with two eventually consistent data platforms and two high availability concerns, etc., but just a single one. And Redis's consolidated database experience has powered a lot of the newer applications that you see out in the world. Well, one of the other reasons why Redis is so popular is because of its simplicity. So instead of shackling you down to tables or JSON documents as the underlying data model to express your problems to the database, Redis provides data structures. You have structures like tables, like hash tables, or you can have JSON documents in Redis. That's no problem. And if those are the best way to express your problem, you can certainly do that. But Redis also provides the ability to have these first-class data types like sets, bitmaps, hyperlog log lists, geospatial types, etc. That fundamentally is much more efficient and effective in expressing your problem. And you can mix and match all of these types into a single database, so your problem can be expressed more effectively into the system. Another important reason that Redis is so popular is Redis modules. This became available with the 4.0 version of Redis, which we shipped over the summer, and is now available in Redis Enterprise products as well. So Redis 4.0 extensibility capability can be used in our products. But what it provides is essentially a way to extend the data types and the methods inside the product without an abstraction. So as opposed to some of the other extensibility mechanisms, Redis's modules bring in new types and new capabilities into the engine and can directly interact and expose their own commands and data types to the end user. We use this technology in Redis Enterprise to do enhanced JSON processing and enhanced indexing for either full text search or geo search or Bloom filters, if you're familiar with those kind of indexes. But there's many extensions that we've built that allow us to provide added functionality on top of the data you have in Redis with this. All right, so let me quickly cover what Redis Enterprise provides on top of Redis open source. We provide great high availability capabilities with Redis Enterprise. So we'll talk about the architecture, and it's got built-in high availability, durability, and DR capabilities into our cluster. Today's topic is very much about this active geo-distributed deployments, but we provide that as part of Redis Enterprise, and robust security capabilities such as encryption of data, authentication and authorization controls, and forensics and event logging. These are some of the things that Redis provides for helping you simplify compliance with either self-imposed or industry-imposed regulations. Redis Enterprise also provides great cost savings. Some of this comes from the enhanced memory architecture that we've developed, which can not only use RAM, but can use local flash drives, SSDs, on your machines as an extension to RAM. This technique allows us to store much larger sets of data in Redis for a smaller infrastructure cost. Obviously, the flash gigabyte price is much lower than the DRAM gigabyte price, and that's where the savings come from. And Redis's flash technology is smart enough to move the right data and place the data that's hot in RAM and warmer in the flash storage. So provides this kind of smart placement and great savings, and without a great compromise on performance. Redis Enterprise's automation support also allows simplified management. Things like rebalancing and resharding, adding and removing nodes, handling failures automatically, just simply handle a lot of the things that administrators have to do that are complex with simplicity. Finally, we provide great added performance on top of Redis with Redis Enterprise. We have some purpose-built indexing that provides search and indexing capabilities in the product on top of Redis data with Redis Enterprise. And the architecture is such that we have built the ability to simply and linearly scale your applications that run on Redis with Redis Enterprise. Let me quickly just show a little bit of the business aspect of what we do. So Redis Enterprise is a mature technology. We run over 550,000 databases on our managed services today. And we provide this database as a service experience on many of the public clouds, Azure, AWS, Google, or SoftLayer. And this product is essentially fully managed. So all you need to do as a developer or DevOps person is tell us which geography and which data center you want your Redis database in, and you get a dial that allow you to either express the throughput or the data size concern you have, and we will get you a Redis database that's fully managed. This product is already running tens of thousands of customers in the cloud and on our free tier, and we have over 7,500 enterprise customers that are paying for this service today. We also provide the same capability of Redis Enterprise as downloadable software. So if you want Redis Enterprise fully under your control, you can download and deploy it. We have over 200 enterprise customers on this product. And this capability essentially takes everything we have on our managed services that's managing the 550,000 databases that we have, and gives you that power in your private data center under your full control. These products have powered many of the Fortune 500 companies, many of the credit card and healthcare companies and communication companies out there. So it's something you can easily trust. Finally, before I switch into the technical material, I just wanted to mention this, that Redis is a modern database that really powers a lot of different use cases. Each one of our data types, each one of our modules have been used to develop applications in one of these different areas. I won't go through each one of them. But what we talk about today, which is active geo distribution, will apply to many of these cases where you simply want either geo distribution and geo redundancy. So if a regional failure takes out your cluster or data center, there's continued business for you. Or in some cases, CRDBs with Redis will power applications that are very hard to develop, that have concurrent write concerns that need to be taken care of. And we'll drill into all of those cases as well. All right, so let me take you through the architecture first in a few quick slides. All right, this is a Redis Enterprise cluster. You will see identical nodes that form the cluster. You can have as many nodes as your database needs in the cluster. There are two paths that are distinct in the Redis Enterprise clusters. There's the cluster management path that you see in kind of the blue layer of this diagram, and the data path, which is the red layer that you see at the bottom. Now, the blue tier is fundamentally called the cluster manager. The responsibility here is mainly to govern the cluster. This is the part of our software that orchestrates operations like adding and removing nodes, automatic failover, migration of shards, creation of databases and distribution of databases, and placement of shards within our cluster for the best throughput and load balancing of the computational capacity you have provided to the cluster. At the data path, we have Redis shards that power these databases that you create in our platform. And it's important to mention that Redis Enterprise is built as a multi-tenant environment, so you can create hundreds of databases in a given cluster. But as management, at this data path, we use Redis shards that are specialized. They're completely compatible with open source. Again, you can change your open source Redis applications connection string to point at us, and it will simply continue to work. But transparently behind the scenes, we're going to shard that database into multiple Redis engines that will power that database, and the administrator gets control to turn up the dial so that there are more shards over time that can power the database as the needs of a given database changes in terms of computational capacity. And we manage replication between these shards so that there's protection against local failures such as node failures, rack failures, or zone failures that will automatically protect you from. One of the more fundamental things to the topic today is the replication architecture. So I just want to spend a few minutes on this. Redis's replication in Redis Enterprise is built on and tuned for these two specific environments. We have local replication that's built for the local area network. Now, the local area network within that cluster, our assumption is that we're in less than a millisecond away between these nodes. The local replication assumes very high bandwidth and low latencies, and we tune our local replication between these nodes for protection against various failures to aggressively replicate all the data immediately to slave nodes, so slave shards that you have in the system. This replication is built to be able to kind of carry as much of your updates to the slave shard, so under a failure you can actually survive. It also is built with Redis's support to be able to write in a way that acknowledges only after multiple shards have received the update. So local replication works with specific commands in Redis, such as the wait command, that will allow you to write either to just one copy of data or multiple copies of data before the write is acknowledged. We also provide a wide area network tuned replication capability. We will actually break this down into two, but the wide area network replication is different because our assumptions are that the bandwidth is lower, we've got higher latencies to travel, and we're on a noisier network. So we're crossing a band boundary, and we assume and expect that there will be failures and retransmits in this kind of network. Now, when we zoom into the WAN-based replication that we have, there are two types that we provide. One is a unidirectional replication. You will see this in Replica. This is basically a CDN-like replication technique where you can actually take a database to many of the geographies. This capability is also possible to set up in a cascading fashion. So you can have a cluster A database replicate to a cluster B, and cluster B database replicate to a cluster C. So you can kind of push the data to the edge and to different geographies using this technique. Now we expect writes to arrive in the master copy of the data, and all the destination databases here are provided as read-only, though there are complex topologies you can set up with this replication technique. More importantly, which is our topic today, is the bidirectional replication that crosses the WAN boundary. So this replication technique is what powers the Redis CRDTs, the conflict-free replicated data types that we have. And it allows writes across all of the copies of data. And it's an active-active deployment. And we'll drill into this more. So I'm going to pause there and start giving you a little bit deeper view of what this technique actually does. All right, let's drill into Redis CRDTs. Before I drill in, I just want to explain this term CRDT. CRDTs is a research topic that has emerged in the last decade and came out of academia, and fundamentally, the technique describes a set of operations and modes that allow the conflicting writes to be handled automatically. And the conflict-free term refers to the fact that these data types are smart, understand the developer's intent, and can infer from what the developer wanted to do to resolve the conflicts in a smart way. And there's a lot of papers on the technique. If you want to read them, our implementation has taken the parts that best apply to Redis data types and have kind of shipped this technology. All right, so let me just first unpack active geo-distributed applications. These are fairly difficult to build, and I just want to kind of put what is difficult about them and how, so far, people have tried to solve this issue. I'm going to use Eric Brewer's CAP theorem as kind of a measuring stick and a classification for explaining some of the existing techniques used by various databases in the world to solve this problem. Just as a primer, Eric Brewer's CAP theorem describes that consistent, available, and partition-tolerant are three important properties of systems. And in his initial work, he theorized that you can only get consistency and partition tolerance, or availability and partition tolerance. So only two of the three properties in your application. I'm going to use the consistency definition and the availability definition he has to describe some of these techniques. So let's take a look at a couple of the techniques people have used in the past to solve geo-distribution across multiple data centers across the WAN. Now, one of the techniques that's been around for a long time is a consensus-driven protocol called two-phase commit. Many of the relational databases have used these techniques. I've worked in the past on two-phase commit myself. These are very consistent protocols. So two-phase commit tries to hit all of the asset properties in many ways, though it has some unpredictability in its nature, but it's proven to be extremely chatty. And WAN traffic and the latencies mean that you can only do a handful of transactions using two-phase commit. It's very, very expensive to do. It provides strict consistency, but by its nature, it also means that it is not available. So two-phase commit requires every participant to be up and running and voting before the transaction can be committed. So any participant being down means you can't really run your transaction. There are other consistent techniques like quorum-based writes. Cassandra is one database that has used this, where you have multiple copies of your data, and you write to more than half the copies of your data, and with that, you ensure, for the most part, that you're going to get a consistent result at the end. This technique also requires, it's a consistent write capability, but it's extremely chatty as well, because it requires you to write to multiple copies across geographies. And by its nature, it's not available, because if some of these copies are offline at the moment, or there's a network partition between the participants, this technique is not going to let you write. So quorum writes fail if participants are down. Now, there's a separate set of techniques that try to achieve availability but compromise on consistency. One of these techniques is called last writer wins. It's very commonly used in a variety of different NoSQL products. Now, last writer wins uses wall clocks to try to decide what is the last write when a concurrent write happens, and decides on the final outcome using these clocks. It's proven to be useful in some cases, but generally a crude technique, especially if you have a large data set and many attributes, like a hash table, where you're editing different parts of the attribute, or a large JSON document. What you find yourself doing is picking one side as the winner, even though maybe there were smarter ways to handle that conflict. There are other techniques called MECC systems. This is multi-version control. If you're familiar with CouchDB, this is what CouchDB has done, which I've worked on in the past as well. MECC techniques are another available but not consistent way to handle concurrent writes across multiple geographies. Unfortunately, MECC systems typically come with very high overhead because it keeps multiple versions of the data, and it leaves the complexity to the end user, to the developer, to program and decide which one of the copies they want to use. It is extremely flexible, but as I said, in terms of performance, it's proven to be extremely expensive and difficult to work with. So in this landscape, this is what CRDTs bring to the table. CRDTs bring a consistency technique called strong eventual consistency to the table. The strong eventual consistency is a definition that's a little bit academic, but at a very high level, it fundamentally means that an ordered set of updates will end up with the same result in your database. CRDTs also provide availability. So unlike the consensus-based protocols like two-phase commit or quorum-based write, CRDTs do not require all participants to be available and up-to-date, available to converse for a write to succeed. So each one of the copies can independently write, and the conflict resolution happens for these complex types behind the scenes automatically based on well-defined set of rules. I know this seems too good to be true, but I'm going to refer to a couple of articles at the bottom here. Eric Brewer, back in 2012, has wrote a great article about CRDTs, describing how his initial CAP theorem made a few assumptions and how he thinks that the rules have changed with the introduction of CRDTs. Another good article to look for is Mark Shapiro's strong eventual consistency definition and his work on conflict-free replicated data types. He's got a couple of videos and presentations you can find from Microsoft Research as well that will explain these techniques. But this new technique, we think, provides the best balance between consistency and availability and partition tolerance in databases. And that's why it will let you build new type of applications with much simpler developer experience. All right, so let's drill a little further into what CRDTs provide. Fundamentally, therefore, active-active geo-distributed applications, our implementation in Redis allows Redis applications to do this with smart auto-conflict resolution that simplify development. I'm going to drill into each one of these words here and give you an overview as to why. So let's start with excuse me, geo-replication. Fundamentally, Redis CRDTs are built on bidirectional replication. So in this picture, you see Redis applications locally working with their local cluster. And in 3 different geographies, we have clusters that have bidirectional replication among them. This fast bidirectional replication is almost as aggressive as the local replication. But from an application standpoint, their experience for reading and writing is just local. So the sub-millisecond latencies that you expect with your reads and writes on Redis, that's fully available to the applications as the network partition happens. All of those clusters can continue to operate. And when things resume, CRDT handles the writes that happened during the absence, automatically understanding the developer's intent. I want to unpack what that smart conflict resolution and understanding developers' intent means a little bit. So another important property is the smart conflict resolution really allows you to build applications that can write across 2 geographies in an active-active fashion. But if for some reason US or European data center was to become unavailable, your traffic can continue and your read and write load can continue to operate with this smart conflict resolution. So let me explain let me explain with an example of a shopping cart here what an auto failover a geo failover would look like across different CRDT participants here, and how CRDTs will handle it. So imagine the case where we have a US data center and a European data center, and we've got a shopping cart, and we're shopping for Halloween. So one of the first things we'll do is, as I'm shopping, is I'm going to purchase a costume and add that to my shopping cart. Now, this is done through a method called sadd. Sadd refers to a set and adding a member to a set. So this specific command is a Redis command that will add a costume item into a cart called cart1. Cart1 is the key. Costume is the item that you're adding to the set. This happens at T1. At T2, our US data center fails. And as a shopper, my experience now is diverted over to the European data center. As I continue shopping on my shopping cart, one thing I should mention before I move on to T3 is that the synchronization has not yet happened. So even though my shopping cart had a costume, that information has not made that over to the European data center yet. But my continuous experience takes me my next addition to my shopping cart of mask to the European data center. So I write another item to my cart. I add another item to my cart using the sadd method in Redis, and this cart1 now contains a mask. So as far as the European data center is concerned, I have one mask in my shopping cart, and the failed US data center assumes that I have a costume in my cart. Once the data center recovers at T4, let's say this was a transient failure, what happens is a synchronization between the US and the European data center. In this case, the CRDTs understand in Redis the intent of the developer. The intent of the developer was to use a set and add new items. So having a costume and having a mask in a set is not a conflicting right. Once these two data centers start speaking with the bidirectional replication we have for Redis CRDTs, they'll understand that there were two unique items that were added to the set. And when they synchronize, they're going to conclude that my shopping cart should contain a costume and a mask. And they're both going to agree that this is the case. So this is what the smart conflict resolution provides, is that there are many cases where the conflicting rights may not necessarily be conflicting if you understand what the developer's intent was. It's not that simple if you have tables or JSON documents, because you can't tell if that's the database system itself can't tell if what your intention with that table is. But in Redis, because we understand the type set or type hash table, we can actually be much smarter about how the developer's set of operations leading up to that moment of the conflicting right should be handled when the consensus and exchange happens. Finally, the Redis CRDTs are extremely simple to develop with because of this CRDT technique. It may seem with the acronyms, etc., that it's very academic, but the fundamental reason we use CRDTs is because developing applications with CRDTs that are active-active is extremely simple, and I'll give you another example here. So all the developers have to do is really use Redis commands to be able to get the CRDT behavior, and we just simply will be able to deliver the smart conflict resolution underneath as the synchronization happens between sites. In this case, I'm looking at a use case where I'm going to be counting, let's say, credit card operations on a credit card called txcounter1. Imagine again this case where you're using the incr method. This is another method that you can use on a counter type in Redis. And I've got a European and a US data center. At T1, I increment in my counter to signify that a new transaction happened on my credit card. At T2, another transaction happens in Europe based on my credit card. I'm an e-commerce fan and happen to be shopping in Europe at T2. But at this moment, the counter increment that happened in US and the counter increment that happened in the EU data centers have not synchronized yet. So if you imagine this case, as far as Europe is concerned, at the moment T2, there's been one transaction in the European data center, and as far as the US data center is concerned, there's been just one transaction. Let's say at T3, to make things a little more complicated, that the US data center receives another transaction on my credit card. When the synchronization happens, because the incr method indicates to us that the operation, the developer's intent was to count these operations, we end up with the correct result of 3. Even though at C3, the US data center thought there were 2, and European data center thought there was only 1 transaction, when they synchronize, they conclude that there are 3 transactions total that happens and agree on that result. In a case like last writer wins, you would have to pick one or the other side, just like the previous example we show on the shopping cart. But in the case of CRDTs, we're smart about understanding the methods you use to get here, which are the incr methods, and we can understand that that method's intention is to really count items so we can accumulate both of your increments across these 2 data centers. So this is a few examples of how CRDTs really simplify life. Let me show you how it actually operates underneath the covers quickly. So as I described, the Redis Enterprise cluster is formed of nodes and is deployed in a single geography, in a single data center. When you have CRDTs, we actually create a globally distributed database in Redis with participating clusters. We call these CRDBs. Technically, in our documentation, they're called conflict-free replicated databases. But once you create this database, what we do is we create local databases in each one of the participating clusters. They're prepared and their replication is set up to exchange all of the updates that are happening in each one of the participants. And once this creation finishes, you get, for each one of the clusters that are participating in the CRDB, a local database, a member CRDB database that your local application can use and connect. So you see 3 applications that are locally connecting and writing and reading from the local databases in this picture. Now, all of this magic happens with this bidirectional replication that we set up, and we use a component called Syncer that manages the synchronization, the bidirectional synchronization that we do. Now, Syncer's responsibility is to send an effective stream across the VAN that is compressed and effectively communicates the incremental state changes that are happening in these types. Syncer uses the writes as they happen on a given Redis Enterprise cluster to a master replica, master shard of your database. And Syncer uses the slave replicas to replicate the information to the remote clusters that are other participants in the CRDB scheme. Syncer is also built to be resumable under failures, so it understands the VAN characteristics and can resume from where it left off if a failure happens, and if a long duration of absence happens. It's also smart to understand that an instance has gone stale, and it will automatically decide to resync a participant if such a long duration failure happens. So before we drill into the demo, I just want to say a quick word about how to develop applications with CRDBs as well. So I'll repeat this, but each one of your Redis applications simply connect to a local database. So in US, North American or South American data centers that you see on this picture, your applications would be deployed locally and read and write to these member CRDBs, those local databases that take your read and write. And CRDB is then responsible to globally distribute those reads and writes that occur to other participants. All of the data set is available in all of the member CRDBs. So if you've got 1,000 or 1,000,000 keys, that's what each one of the participants will have. And all of that data is available for read and write on all of the geography. So this is what the active-active capability means. Now, the beauty here is that aside from a small few changes, your Redis applications can transparently use CRDBs. You still can use the sets or the hashes or the excuse me, string types, just like you do in Redis. There's a few things to understand. Obviously, the conflict resolution rules are important to understand for you to develop applications, but from an app standpoint, fundamentally, the Redis experience is not very different. You can use any of the Redis SDKs that are out there for you to develop these applications. So if you're a Python or Java fan, you can just use the existing Redis clients. And the smart conflict resolution is something we explain in our documentation deeply, so you can get assurance that when you use specific methods on sets or hashes or strings, you can greatly understand with examples how the conflicting writes are going to be resolved and how they're going to be communicated between different shards. Fundamentally, the communication among these data types, each data type and its methods really drive how we resolve conflicts when they happen based on the methods that developers call. So sets resolve conflicts different than hashes, and strings use a different set of techniques. And using the specific data type and the specific methods infer to us what exactly you were trying to do. And our CRDT replication between these participants take these methods, and that's what they replicate in some ways is the understanding of these methods that you've called, and that's why we can preserve your intentions as we're resolving the conflicts. So that's kind of a high-level application viewpoint of Redis CRDTs. All right. I know I've given you a long description of this technique and some of the capabilities, so let's take a look at how this works in real life. One thing I want to start with here.
Sorry, Jihan, to interrupt you. Do you have time for one question before you start the demo, just for clarification?
Of course. Please go ahead.
Great. So do all CRDB clusters need to be online for read and write operations to succeed in each data center?
That's a great question. No. So in the case of CRDTs, just to kind of go back to this picture, if one of these clusters or two of them are not available, the remaining cluster can continue to read and write. So there is no requirement other than the local cluster being available for an application to reach in and write. So there's no consensus, there's no quorum requirement at a high level here that would require that. So yeah. All right, let me get back to the demo. I just want to show you. I'm running Docker. This is going to be purely on my laptop, so bear with the performance that you're going to see here on some of these things. But I'm running two clusters that are running in two individual containers. They're just single node clusters, so we're simulating something fairly scale minimized here. But there's a cluster one that is just one node that's running Redis Pack, and a cluster two that's running Redis Pack. Let me show you what that cluster looks like really quickly. So here is a quick picture of what a cluster, Redis Enterprise cluster looks like. This is, if you look at the configuration, this is called cluster1.local. It's running our Redis Enterprise 5.0 version, and it's just has this one node. This UI gives you a good overview quickly of how things operate. Just want to show you this Redis database that is locally exposed here called sample CRDB. One of the things about this local database is that it actually exposes an endpoint at port number 12,000. In fact, all of the local databases on two of these clusters will actually have port 12,000 as their port. So the CRDB, when it was created, will actually push the same port number to each one of these databases. Now, one thing that's unique about this database is that it has a section called participating clusters that express both the local cluster and the remote cluster that we're synchronizing with. The synchronization here represents the status of the synchronization at a very high level, but we're synchronizing with another cluster called cluster2.local. And this database, even though this is the local copy that we're looking at, is actually synchronizing across these two clusters. If I go to cluster2.local, you will see the same picture, except the synchronization sign will be up here at the top because the local cluster does not have a synchronization sign. But this is kind of a quick view of what this looks like. So let's drop the command line. So let me explain these bottom two windows. I'm on cluster 1 and cluster 2. In the picture, the green and the blue panes here represent those two clusters. What I'm going to do is I'm going to simulate some writes. We'll take a look at how the system behaves. I'm going to break their network so that they can't communicate with each other. So we'll simulate a failure here of the WAN, and we're going to do some writes across both of them and see how the conflict is resolved at the end. So let's start with just testing what we have here. So I can set a key called key1 to A. If I do get on that, that's locally here, and this excuse me, this cluster has the key1 set to A. If I do a get here on key1, it returns the same thing, so the synchronization has succeeded. If I actually do set on a key1 to set this to B, I should actually see that happen on the cluster on the left side in the green pane as well. So good, replication is happening, and these two clusters, these two databases are synchronizing on two independent clusters. Now, one of the things I could actually do is I could do an incr on a key2, I could actually do that a couple of times to increment the value. So if I actually do this now, I see the value 4. If I do that here, I see the value 4 as well. So let's inject some failures here. So I'm going to partition the network between these two. What I'm doing is basically providing some IP rules to prevent the communication between them. So this essentially means these two clusters can't communicate anymore. I can still read key2, no problem, on either side. But if I start incring on key2 in an isolated fashion, I've actually done that a few times now. I've gotten up to 9 here. That information is not going to get to the other side. So if you look at the green window, we're still returning 4 because the replication has not happened. So let's do something interesting here. Let's increment here too, but let's increment to number 7 here. So what happened is the last time we agreed on the value of key2, we decided the value was 4. Since then, the green side has incremented the value 3 times to 7, and the blue side has incremented the value 5 times to 9. So the result that will happen when we synchronize should actually take into account that the starting value was 4 and only a total of 3 plus 5, 8 increments have happened. So instead of, I guess, compounding 7 plus 9, we should actually end up with the correct incremented number when we synchronize. So let's restore the network. What this is going to do is that the synchronization between these two clusters are going to resume, and once the syncer realizes that the network is up, it will automatically reconnect and resynchronize. So if I do a get on key2, now I see the value 12. That's a good sign on both sides, because they were both aware of the fact that the end result shouldn't have been 7 plus 9, which is 16, but should only accumulate the number of increments that happened while they were offline. So this is the magic of CRDTs happening on a type like counter here that you can see. So we understand that this is a counter type. We understand that you've used the increment method during your absence, during the absence of replication, and we're smart about how we replicate this counter. Let me show another quick example here. Let's clear the screens of sets. So we're going to use a set called S1, and I'm going to add A, B, and C into the mix. So if I get members of set 1, you will see there A, B, and C. If I do that here, I should see the same results. Perfect. Let's break our network again. Now, if I use the sadd method in the set to add another member called X, I'm actually now going to see X added to the list of members here. However, on the green side, because the replication is no longer able to replicate, we don't see X. But let's add another item here called 9 into the mix. Now, I'll see A, B, C, and 9 on the list. If I restore the network between these participants, again, the syncer will realize that the replication is up. And as I look at the results, once the syncer realizes that we have both sides enabled to replicate, I should actually see X, which is a unique member, show up on the green side, and 9, which is a unique member, show up on the blue side. And we should have both X and 9 added to the list of A, B, and C on the mix. Sorry, it looks like I actually broke the network, but never restored it. Let me do the restore here. All right, now you can see that 9 and X are both on, the blue side hasn't received it yet. All right, finally. So you can see that all 5 members now show up on both sides here. All right. That was my demo. So a very quick recap here. Today we talked about Redis and Redis Enterprise architecture, the replication capability that allows us to build Redis CRDTs, and how CRDTs operate and provide the active-active deployment topology, smart conflict resolution, and with all of that, a simplified development experience for you to develop these complex geo-distributed applications. You can get started today if you want to try this technology. I was using just Docker images. You can go download Redis Enterprise 5.0 on our website for Ubuntu, Red Hat, Oracle Linux, or Amazon Linux. Or if you're a Docker fan, you can start using our Linux-based containers on Mac, Windows, or Linux systems today. With that, I'm going to open it up for questions.
Great, thanks, Jihan. So for CRDTs, is there a minimum quorum required?
No, so CRDTs, when they're deployed, you know, however many participants you have, as long as you have one cluster up and running, things will continue to operate. So even if you have a CRDB deployment across 5 data centers, you can continue to read and write to the last copy that's available. So we do not require any quorum or a number of clusters to be up and running that's larger than more than half of the participating clusters.
And what flavor of CRDTs do you use, operation-based or state-based?
That's a good question. So when you listen to a lot of the academic talks and other implementations, you will see this distinction of state versus operation-based CRDTs. We actually use a mix of two. The reason I say that is there are moments in time where we have to do a full synchronization. If one of the participants have disappeared for a couple of days and things have changed so much that it is more efficient to send the full state of the CRDT, all the keys that we host, then we may actually use a state-based replication technique and send the data as it is. But in steady state, we actually use an operation-based CRDT technique. So what we're doing effectively when communicating with the bidirectional replication is use the operations and the incremental changes that have happened to the data, and not the full state of the data every time. And because of that, for example, in the example of the set, the communication effectively is keeping some additional metadata, but fundamentally is replicating the fact that X or 9 was added to the set, not the full state.
Great. I believe that is all we're going to have time for today. But before we go, Jihan, I just want to quickly throw it back to you for one final thought or one key takeaway you'd like to leave the attendees with today.
Yeah, I hope this was a good recap of some of the existing techniques and difficulties of building geo-distributed applications, and I hope everybody got a chance to at least get a glimpse of what CRDTs provide, and I hope everybody goes and downloads the capability and gives us feedback on this technique.
Mm-hmm. Great. Well, thank you for a great presentation today. Again, that was Jihan Bikolu, Vice President of Product Management at Redis Labs. And I would like to thank Redis Labs for sponsoring today's webinar, as well as the attendees for joining us today. Until next time, I'm Christina Cardoza with SC Times.